Hello, my name is Simon Mead, and this is my Triple E 120 Capstone design project. Okay, so first, start out with the stakeholders, James Garvey, my teacher, Calp, my TA, and Aaron Mead, my mother. The general consensus was that they realistically wanted some computer that was more automated, and then they didn't really want there to be long cooldowns, but they also wanted the computer to run longer. So I came up with two solutions, which is that one solution basically runs the computer to its maximum, but it will fail a lot of the time and it'll run to error, and it has to have a longer cooldown for that reason. But my second design is that you're forced to go back to the default state if you try to switch from accelerated to fast, that you can't maximize output. But it allows for a lesser cooldown, and you can, in theory, go infinitely um, on this computer if you just kept switching between acceleration and then default and then fast, or fast then default then acceleration. And so yeah, so that's like the interview stuff. Here's my state definition table for my design one. Here is my diagram for my state one. Um, Here is the design one transition table. And then here are the Karnoff maps plus the equations. Quickly go through these. You'll have all of them. So, okay. And then the first design ends up using, we'll just go to the totals, 11 OR gates and 14 AND gates. So it's going to be, well, you don't know, but it's going to be a more simple design than number two. Number two had a different style of encodings because I wanted to be more centralized, because I thought that this would make um, the math easier. I think it did actually end up helping a little bit. Here's my transition table. Here's my diagram. These are the equations. You'll get to see those, so I don't need to go through them. Um, and this one ends up using a total of 13 OR gates and 20 AND gates. So definitely more expensive, but overall, uh, my criteria were sharing the computer. I made that a big one because I thought that it was going to be very important. Simplicity was pretty big as well because I wanted to be easy to make. Performance allowance was, still there because people want performance. Time to cool down was pretty important because we wanted them to be cooled in a faster time period, and then the amount of automation. Um, Applying the criteria to pit. Oh, okay. So I applied the criteria, and the second one got a 7 out of 10, which was better than the first one. The first one got a 6.15. Um, and then, uh, 'cause I redid the math. And then the simplicity, because it wins in simplicity and performance, but uh, computer two wins in the strength of the computer, which was a lot of the weight. So that did much better in that category, as you can see, getting a 9 in that category. And this is the final design, which I will now go demonstrate. Okay. Oh, you don't have anything. All right. I don't demonstrate it. Okay. So, um, I'm just gonna quickly demonstrate how it works. Okay. So, we have, let's zoom out a little bit. We have the clock, we have the reset, and let's say I want to go to the fast state, right? I clock, it goes to default first, and then it goes to the fast state. And then if I click a couple times, it reaches the fast state and then eventually reaches the error. And then if you keep going, it'll just start a cooldown. Now let's say I want to go to acceleration, right? I clock, it goes to acceleration, it does it twice, and then there's an error. And then we go back to a cooldown. But the cool thing is let's say I go to default and then I go to acceleration. Well, let's say I want to go to fast now. I then have to go back to default first, and then I can go back to fast. And let's say I'm in fast, I'm going to go to acceleration. Well, I have to go back to default, and then I can start accelerating. So in this way, you can honestly go on forever with this design, and I thought this was a good idea overall. The reset works just to show you that it works. Puts it back at 0. And then just a little bit about the design. You know, it's pretty basic. You have your cues over here. You have your uh, which go into here, and then that is transitioned to here to create, and then back into here for the Q plus for Q plus. These are all the Qs. These are Q2, Q1, Q0, which are then connected by these tunnels. And then those are sent into these, which then give the output. This is just the output. Um, it's just the output logic, right? We can zoom in on all that. And then we can come over here and we can zoom in on Q2 and Q1 really quickly just to show you what they look like. So Q2 is pretty big. And let's go down Q1 and then Q2. That was my capstone. Thank you very much. And yeah.